In this section, we're going to look at work, which will lead us into power and energy. First of all, work is going to be calculated by taking force times displacement. Now we have to remember displacement is the change in position. So that's going to be important. Also, because displacement is a vector, work will also be a vector because we will have to take into account direction. So your equation here, work equals force times displacement. So if we look at a couple scenarios, we have to look at the application of the force or which way something's moving because of that force. So we might have somebody lifting something up or setting something back down. They might be pushing an object one way or they might be pulling it another. So all of those things are going to come into play when we are looking at work. If the object moves one way, let's say maybe the object moves to the left, but the only force acting on it is the weight down, which would be weird if the force and the way that the work moves are not in the same direction, then we wouldn't have any work done. Also, if the force is applied, but the object is not moved at all, or if it returns to the same spot that it started out in, no work is also done because displacement would be zero. So if you were to pick up a weight, like the guy in the previous picture was lifting weights, if you pick that up and put it back down, the displacement of that object is zero, so the work done would be zero. Unit for work is the joule. So if we consider this, you're pushing against a wall of a building. Are you doing any work? Well, we're going to assume that that wall is not moving. So if the wall doesn't move, the displacement zero, so your work done is zero. Which would require more work, lifting a 50 kilogram sack 2 meters or lifting a 25 kilogram sack 4 meters? Well, first of all, we would need to know the force. So the force is actually going to be the weight of the object. So for the first scenario, if we had 50 kilograms multiplied by 9.8, that's going to give us 490 newtons. And for 25 times 9.8, that's going to give us 245 newtons. And so we're lifting those up. So 490 is my force times my displacement of 4, or 245 times, oh sorry, this one was the 2 and this one was the 4. We're going to get the same answer. So 980 joules here and 980 joules here. So in this scenario, the same amount of work would be required. Calculate the work done when a force of 1 Newton moves a stack of books 2 meters. So if he's pushing this direction on the books, he's applying a force of 1 Newton. The books move that way 2 meters, so the work done would be 2 joules of work. Okay, here we've got a frog pushing a shopping cart. For this situation, we're going to not think about him pushing it at an angle. We're going to assume he's pushing it in a straight line, just to simplify things. Later on, we will consider angles. So he's pushing this shopping cart. He is applying a force of 20 newtons, and he's pushing it 3.5 meters. So our work done would be 70 joules. Calculate the work done in lifting a 500 Newton barbell 2.2 meters above the floor. So we would just do 500 times that 2.2, and that would give us 1100 joules. Now, if it had said he lifts it and sets it back down, the displacement would be 0, so there would be no work done. Now for angles. Again, we just have to remember our sine, cosine, tangent. So we all should be getting very good at this point. Still using work equals FD. So now what we have to look at, if the force is at an angle, so the man here is pushing on this lawnmower at an angle, but the lawnmower is moving horizontally. So the force that's actually making that lawnmower move forward is this X component of the force that the man is exerting. So this part of the force, the X component, is what we would use when we would solve for our work. So let's try this. We've got a man cleaning his apartment. He's pulling a vacuum. So this will be the main part of the problem down here. Okay, so he's pulling that with a force of 50 newtons at an angle of 30 degrees. So that means this is 30 degrees. A force of 40 slows the motion, and the vacuum is pulled a distance of 3 meters. So we're going to say that our distance, our displacement is 3. So if he's pulling it like that, friction will be this way. So that's 40 newtons. So we need to find the X component of the force. So since here's our angle, we're going to use cosine. So 50 cosine 30. And so that gives me 43.3. So it wants to know the net work done on the vacuum. Well, we need to know the net force. So if we've got 43.3 going that way and 40 going the other way, our net force is going to just be 3.3 because we would subtract those two. So the net force is 3.3. So the net work would be 3.3 times 3, or 9.9 joules. Here we have a shopping cart. So the shopping cart is being pushed with a force of 35 directed at an angle of 25 downward from the horizontal. So we're pushing it like this. So our angle would be here at 25. Let me draw it a little bit over here so we have more room. So this is 35. Our angle is 25. We are needing to find the X component of that. So 35 cosine 25 is going to give me 31.7. Find the work done by the shopper as she moves down a 50-meter length aisle. It doesn't tell us anything about friction, nothing else. It only gives us that force. So that's all we're going to work with. So the 50 times that 31.7 will give us our work. And we get 1585 joules. Last one, we have a man moves a broom horizontally by pushing it with a force of 80 directed at 50 degrees. So he's pushing it with 80 newtons. So the angle there is 50. So the x component of that is going to be 80 cosine 50. So 51.4. When he stopped moving, he had done 450 joules of work. How far did he push the broom? So if we've got 450 joules for our work equals force, which is the 51.4 times our displacement. So we're going to take 450 divided by 51.4, and that gives us a displacement of 8.75 meters.